Hi, it's Mr. Mac, and we're looking at the module From the Universe to the Atom, and our third inquiry question, which deals with the quantum mechanical nature of the atom. So what is the inquiry question? How is it known that classical physics cannot explain the properties of the atom? What we're going to learn is to analyse the quantum mechanical nature of the current model of the atom, and we'll be able to assess the limitations of the classical model of the atom. Well, what are the limitations of the Rutherford model of the atom? The motion of the electrons in the Rutherford model was unstable because, according to classical mechanics and electromagnetic theory, any charged particle moving on a curved path emits electromagnetic radiation continuously. The resulting loss of energy by the electrons caused the electrons to spiral into the nucleus in a very short amount of time. In other words, atoms cannot exist. Now clearly, atoms do. So the classical theory must be wrong. To remedy this stability problem, Bohr modified the Rutherford model by requiring that electrons move in orbits of fixed size and energy. The energy of an electron depends on the size of the orbit and is lower for smaller orbits. Radiation can occur only when an electron jumps from one orbit to another. The atom will be completely stable in the state with the smallest orbit, since there is no orbit of lower energy into which the electron can jump. So Bohr used the Rutherford model of the atom as his starting point. He then had two postulates that acknowledged experimental evidence related to spectral emissions. Electrons were allowed in certain stable circular orbits so that the electron's angular momentum was quantized. The electron in a stable orbit did not lose energy by the emission of electromagnetic radiation. Bohr assumed that classical electromagnetic theory was not valid for atomic systems. Now, in the Bohr model of the atom, electrons exist in one of a number of stable energy states. Electrons move from lower to higher energy levels when they gain energy from a photon. Electrons emit energy as photons when they move from higher to lower energy levels. This is consistent with the law of conservation of energy, which states that energy can neither be created nor destroyed, only transformed from one type of energy into another. Energy is conserved because the absorbed or emitted photon energy is equal to the energy difference between discrete electron energy levels. Well, Bohr had the following postulates. For some orbitals, the laws of electromagnetism do not apply. And secondly, an atom can exist in certain allowed or stationary states, with each state having a definite value for its total energy. The total energy of an orbiting electron is quantized such that its angular momentum is given by L, for angular momentum, equals mvr, where m is the mass of the electron. And that equals n, which is a positive integer, times h, Planck's constant, divided by 2 pi. And thirdly, an atom emits or absorbs energy only when an electron moves from one stable orbit to another. In transition from initial to final state, a photon is emitted or absorbed with the energy delta E equals the absolute value of final energy minus the initial energy, which is simply equal to HF. Well, here are some limitations of the Rutherford-Bohr model of the atom. Bohr's theory could not explain various spectra of atoms with more electrons. It worked really well for hydrogen, but not for other elements. Secondly, it couldn't explain whether or not elliptical orbits are possible. And thirdly, the arrangement and distribution of electrons in various elements, such as 2 in the inner shell, 8 in the next shell, and so on. Bohr's theory could not explain the fine structure of certain spectral lines of hydrogen, which is called the Zeeman effect. More of that a little later. Couldn't explain the relative intensities of spectral lines. Couldn't explain how electrons also have a wave nature, and we'll look at that a little bit later. couldn't explain the time that an electron spends at any given state, and how an electron could have both a known radius and a known orbit, which is contra Heisenberg's uncertainty principle, and couldn't explain the ground state orbital angular momentum correctly. Now, you've probably used this in the school science lab, where we've got a spectroscope made with plastic and has a scale on the inside and an eyepiece to look through and a diffraction grating. And on the right-hand side, this would be set up as a demonstration. That discharge tube is filled with hydrogen, and high voltage is put through the hydrogen to make it glow. And when you look through the spectroscope, you will see visible lines for the emission spectrum. And this is the hydrogen discharge tube. And when light's emitted by a sample of excited hydrogen atoms, it's split into its component wavelengths by a prism or diffraction grating. And there are 4 characteristic colours that show in the emission lines: violet, indigo, aqua, and red. And the most intense is the red at 656 nanometers. We can actually calculate these wavelengths very easily by using a formula discovered by a scientist called Johann Balmer. So here's the emission spectrum of hydrogen, and we can notice the certain colours and the specific wavelengths, with red at 656 nanometers, aqua at 486 nanometers, indigo at 434 nanometers, and violet at 410 nanometers. What do you notice about these numbers? Probably not a lot, and it took someone like Johann Balmer, who enjoyed playing around with numbers, to find a pattern. And here's the pattern. If you take the wavelength and determine the frequency in terahertz, and then take that wave number and get a number that is 2,743,902 and divide it by that wave number, you'll end up with a fraction in whole numbers. So 1.8 is 9 divided by 5. 1.3 is 16 divided by 12, and then 25 divided by 21, and then 36 divided by 32. And you'll notice that 9, 16, 25, and 36 are all perfect squares, and the 5, 12, 21, and 32 are all simply 4 less than those perfect squares. So here's the emission spectrum again. And the emission spectrum of hydrogen has 4 visible lines, as we know. The Bohr model for the electron transition in hydrogen between those quantized energy levels with different quantum numbers n yields a photon by emission with quantum energy E equals hf, which is the difference between the 2 energy levels, E2 minus E1. The wave number, which is simply the inverse of the wavelength, 1 on lambda, equals r times, in brackets, 1 on nf squared minus 1 on ni squared, where r is the Rydberg constant. And this is what Balmer used to find out the whole number relationships. So let's look at a worked example. Here it is here. Calculate the wavelength of light emitted by an electron moving from energy level 3 to 2 in a Bohr model hydrogen atom. And I put the spectra of the emission of hydrogen just there to remind you. And the first step is always data. It's a calculation question. Ni, the initial number, is 3. Nf, the final number, is 2. And the Rydberg constant, 1.097 times 10 to the 7 per meters. And here's the formula, straight from the formula sheet. You don't have to memorize it. And simply substitute. And notice how simple the substitution is. So we put in R, 1.097 times 10 to the 7. And in the brackets, can you see the substitution? 2 and 3. And then it's a simple matter of calculating. In fact, you could do it possibly in your head. 1 on 2 squared is a quarter. 1 on 3 squared is a ninth. And you end up with this number here. Just make sure you can correctly do this on your calculator. And when you flip it over, you get 6.563 times 10 to the negative 7 meters to 4 significant figures. And note that this is the thin red line at 656 nanometers. Well, let's try another worked example. Here it is. Calculate the shortest limiting wavelength for hydrogen. Oh, that's it. Doesn't seem to be any numbers. But let's think about this more clearly. The limiting wavelength is when n approaches infinity. And so in the data we have, NF, the final number, is 2, where the electron orbits at n equals 2 level. Remember, we're dealing with the visible emission spectrum and the Balmer series. Ni is infinity. Now, we can't substitute infinity into an equation, but we do know that as n approaches infinity, 1 on n approaches 0. So here's our formula. And we can simply substitute. So the Rydberg constant times, in brackets, 1 on 2 squared, and instead of 1 on ni squared, that whole fraction becomes 0. And that's nice and simple. We can find out what 1 on lambda is and then flip it over and find the answer is 365 nanometers to 3 significant figures, which is ultraviolet. In other words, it's invisible. So this means that when an electron goes from the shortest wavelength, the limiting wavelength for hydrogen, and falls down into orbital 2, it will give out a photon with lambda equals 365 nanometers. Well, Balmer wasn't the only one who came up with a series. Scientists by the name of Lyman discovered an invisible set and a series of orbitals where electrons fall from orbital 6, orbital 5, orbital 4, orbital 3, orbital 2, all the way down to orbital 1. Now, they're not detected on our spectroscope in the school laboratory because they're invisible ultraviolet. But here's an example. Calculate the wavelength emitted in the Lyman series when an electron returns from energy level of n equals 6. And you can see from the diagram how it can go all the way from n equals 6 all the way to the inner circle or the inner orbital n equals 1. Here's the data. NF equals 1, Ni equals 6, and there's the Rydberg constant. And again, we simply substitute. To get 1 on lambda is 10,665,277. Flip it over, and we've got 93.8 nanometers to 3 significant figures. And that's ultraviolet. Now, you don't need to know ultraviolet, the color, or where it is on the electromagnetic spectrum in order to answer this question. But then a scientist by the name of Paschen came up with another series, and let's have a look at this one. It says calculate the wavelength emitted in the Paschen series when an electron returns from energy level of n equals 6. Now, the Paschen series, the electron falls to n equals 3. Here's the data. NF equals 3, Ni equals 6. There's the Rydberg constant. There's the formula, and we simply substitute. So even though the formula looks very complicated, the actual calculation is quite straightforward. And we flip over the 1 on lambda to get the wavelength 1.09 times 10 to the negative 6 meters to 3 significant figures, and that's infrared. Again, you don't need to know that it's infrared to answer this question. Well, here's Louis de Bruys' explanation. The Bohr model of the atom did still have a major issue, that the orbiting electrons did not emit radiation. Bohr simply ignored this issue and stated that they didn't, but an explanation was required. And it was Louis de Bruy, and please note he's a Frenchman, and the pronunciation of his name is de Bruy, not de Broglie. Louis de Bruy first came up with an explanation based upon the idea that, just like light, electrons could act as both particles and waves. It was in the form of a standing wave that the electron took within the atom with no loss of energy. And here's
Louis de Bruy.
a Frenchman pronouncing Louis de Bruy's name.
Louis de Bruy.
And here are some diagrams that show a visual representation of Louis de Bruy's theory. So here is de Bruys' justification of Bohr's assumption. Louis de Bruy, a French physicist, came up with the explanation for why angular momentum might be quantized in the manner Bohr assumed it was. He realized that the wavelength associated with the electron, and assuming an integral number of wavelengths must fit in the circumference of an orbit, there is a quantized angular momentum that can be found. So Bohr used E equals mc squared, Einstein's famous energy mass equivalence equation, which is the same as E equals mv squared for any velocity. And he also used E equals hf with Planck's constant times frequency, which is E equals hv on lambda, just replacing with the wave equation, and he equated them to get mv squared equals hv on lambda. Rearranging, he found lambda equals h on mv, which is called the de Broglie wavelength. Since the circumference of a circle C has an integral number of wavelengths, C equals 2 pi r equals n lambda, where n is a positive integer. This becomes 2 pi r equals nh on mv, and this gives the Bohr relationship mvr equals nh on 2 pi, which is angular momentum L. Well, according to classical physics, electrons should behave like particles. They travel in straight lines and do not curve in flight unless acted on by an external agent, like a magnetic field. In this model, if we fire a beam of electrons through a double slit onto a detector, we should get two bands of hits, much as if you were rolling marbles to a wall that has two holes in it. But what we found in practice is that there is destructive and constructive interference, and we end up with bands of hits detected. This shows and provides evidence for the wave nature of electrons. So de Broglie's hypothesis to explain this theory of atomic structure, he proposed a bold hypothesis that subatomic particles of matter sometimes act like waves and sometimes like particles. The dual nature of matter is similar to the dual nature of light. De Broglie proposed that this relationship mvr over nh on 2 pi would determine the wavelength of any matter. This wavelength is called the de Broglie wavelength. According to de Broglie, firstly, nature loves symmetry, so matter and radiation are two forms that exist. Secondly, that matter and energy must be mutually symmetrical. And thirdly, particles of matter should also exhibit wave-like properties. So how was de Broglie's hypothesis tested? Although de Broglie was credited for his hypothesis, he had no actual experimental evidence for his conjecture. In 1927, physicists Clinton Davison and Lester Germer of Bell Labs performed an experiment where they fired electrons at a crystalline nickel target. Davison and Germer designed and built a vacuum apparatus, which you can see in this photo, for the purpose of measuring the energies of electrons scattered from a metal surface. Electrons from a heated filament were accelerated by a voltage and allowed to strike the surface of nickel metal. The experiment showed that electrons behaved like waves in that they exhibited a diffraction pattern when they scattered off the crystalline structure of the nickel target. The resulting diffraction pattern matched the predictions of the de Broglie wavelength. The Davison and Germer experiment showed the wave nature of matter and completed the theory of wave-particle duality, one of the underlying principles of quantum mechanics. De Broglie received the 1929 Nobel Prize for his theory, the first time it was ever awarded for a PhD thesis, and Davison and Germer jointly won it in 1937 for the experimental discovery of electron diffraction, supporting de Broglie's hypothesis. Here is a plaque on the original location of the Bell Telephone Labs. And here's an image of an ant in a scanning electron microscope based on the wave properties of electrons. An electron microscope uses a beam of accelerated electrons as a source of illumination. Since the wavelength of electrons can be up to 100,000 times shorter than that of visible light photons, electron microscopes have a higher resolving power than light microscopes and can reveal the structure of smaller objects. A transmission electron microscope can achieve better than 50 picometers resolution at magnifications of up to about 10 million times magnification, whereas most light microscopes are limited by diffraction to about 200 nanometers resolution and useful magnifications below 2000 times. Well, what about the Zeeman effect in hydrogen? When an external magnetic field is applied, sharp spectral lines, similar to the transition from n equals 3 to n equals 2, split into multiple closely spaced lines. This first observed by Peter Zeeman, this splitting of spectral lines in hydrogen is attributed to the interaction between the magnetic field and the magnetic dipole moment associated with the orbital angular momentum. In the absence of the magnetic field, the hydrogen energies depend only upon the principal quantum number n, and the emissions occur at a single wavelength. So let's look at a worked example to do with the de Broglie wavelength. The question is to find the de Broglie wavelength for an electron moving at the speed of 5 times 10 to the 6 meters per second. Well, it's a calculation question, so the first step is data. V, we're told, is 5 times 10 to the 6 meters per second. But we also know the mass of the electron, 9.109 times 10 to the negative 31 kilograms, and Planck's constant. Here's the formula. Lambda equals h over mv, the de Broglie wavelength. We simply substitute. Planck's constant on top, mass of electron on the bottom, and the velocity on the bottom. And when we calculate, we find 1.45 times 10 to the negative 10 meters, correct to 3 significant figures. Well, if it's true for electrons, what else is the de Broglie wavelength in calculation true for? So here's another question. Find the de Broglie wavelength of a 3 kilogram object moving with a speed of 3 meters per second. Here's the data. V equals 3, m equals 3, there's Planck's constant, and there's the de Broglie wavelength equation. And we substitute. Again, Planck's constant on top, 3 times 3 on the bottom, and we end up with a wavelength of 7.36 times 10 to the negative 35 meters, correct to 3 significant figures, which is incredibly small and very small to notice. Well, what are some failures of the Bohr model? Well, we've seen some already, and here are some more. While the Bohr model was a major step towards understanding the quantum theory of the atom, it is not in fact a correct description of the nature of electron orbits. Some of the shortcomings are that it fails to provide any understanding of why certain spectral lines are brighter than others. There's no mechanism for the calculation of transition probabilities. And the Bohr model treats the electron as if it were a miniature planet with a definite radius and momentum. This is in direct violation of the uncertainty principle, which dictates that a position and momentum cannot be simultaneously maintained. So we'll now look at Schrödinger's contribution to the current model of the atom. In 1926, Edwin Schrödinger, an Austrian physicist, took the Bohr model of the atom one step further. Schrödinger used mathematical equations to describe the likelihood of finding an electron in a certain position. The atomic model is known as the quantum mechanical model of the atom. Unlike the Bohr model, the quantum mechanical model does not define an exact path of an electron, but rather predicts the probability of the location of the electron. The model can be portrayed as a nucleus surrounded by an electron cloud. Where the cloud is most dense, the probability of finding the electron is greatest. And conversely, the electron is less likely to be in a less dense area of the cloud. Thus, this model introduced the concept of sub-energy levels.